Welcome everybody. Today's video is going to be on 7.2, general results. Now remember, we're talking about eigenvalues and eigenvectors, so we're going to learn some general results about these things, continuing on from where we left off in 7.1. So we start off with a new definition. So first, let A be an n by n matrix and let's suppose, and let me actually back up here. Let me say that it has eigenvalues lambda 1 to lambda k. Okay, so it's got k eigenvalues. For each eigenvalue, lambda I, we're going to define EI as follows. EI is defined to be the set of all V such that AV is equal to lambda I times V. Okay. We call EI the eigenspace of A corresponding to eigenvalue lambda I. So let's look at this EI. This looks like the set of all eigenvectors, doesn't it? However, there's an important distinction here. We're not calling the eigenspace just the set of all eigenvectors because that does include the zero vector. We did not exclude that. So let me just do a few notes. So note 1. EI is defined to be the set of all eigenvectors with eigenvalue lambda I together with, that's a union symbol, together with the zero vector. Okay, so in 7.1 we were finding this set, but we were finding this first set, but we were always excluding the zero vector. But for the eigenspace, we do include the zero vector. Why would we include the zero vector? Well, we include the zero vector because that actually turns it into a vector space, right? We cannot have a vector space without the zero vector. So this will be note 2. We have seen this before. So note 2, if T is the linear transformation given by T of V is equal to A minus lambda I times V. Oh, sorry, I messed up there. I need to write it this way. Okay. Then the kernel of this transformation is actually the same as the eigenspace, right? It's all of the vectors that make that true. And that is also the same as the null space of a minus lambda I. Okay? So this is what we have, which is in fact a subspace, right? What is it a subspace of? Well, where do these vectors live? Remember, these are all vectors, and we know that vectors can have complex numbers. So let me just say that they live in Cn, or sometimes Rn, if you're lucky. But I'll just say that they for sure live in Cn. Let's keep going with some observations, okay? So observations. What do we know about the characteristic polynomial? Okay. Remember, the characteristic polynomial is defined, I want you guys to recall what this is. The characteristic polynomial is the determinant of a minus lambda times I. Okay, so you take the determinant of that matrix. Now, let's think about these polynomials, okay? These polynomials, depending on lambda, right? Lambda could be complex. And so this guy is a polynomial of nth degree from the complex numbers. Okay? So what do we know about nth degree polynomials? Well, by what we learn in algebra, this is the most important theorem in all of algebra. So by the fundamental theorem of algebra, if lambda 1 to lambda k are now, let me just point out that these are complex numbers. Some of them might be reals, but recall that reals are a subset of the complexes. So I'm just going to write it this way. If lambda 1 are the k distinct eigenvalues, then sorry, I have a little typo here, fundamental. Then P of lambda always looks like this. Negative 1 to the n, lambda minus lambda 1 to the m1, lambda minus lambda 2 to the m2, lambda minus lambda k to the mk, where each mi is equal to the multiplicity of lambda I, and all of those mi's have to add up to n. Again, how do we know this? This is called the fundamental theorem of algebra. It says that anytime you have an nth degree polynomial, you can always factor it into its roots, and the roots are going to look like this. You're always going to have a negative 1 to the n. That's true because of how the determinant works. But you're always going to have a negative 1 to the n. And then you're going to have lambda minus each root, and it appears a certain number of times. And we know that if you add up all the times that those things appears, they have to add up to the degree of the polynomial. Okay? All of this is going to become important with some terminology in a moment, but we're going to do an example. Okay, so let's do an example. determine all eigenspaces for the matrix A as well as their dimensions. Okay, it's just a 2 by 2 matrix. This one should not be too tricky. So we're going to begin by, the same way we start every eigenvalue problem is we want to start by finding the characteristic polynomial. So P of lambda, remember, is equal to the determinant of, we're going to take lambda away from the diagonal elements, right? So when you take the determinant of this, you get negative 3 minus 2 lambda plus lambda squared minus 5. Okay, because if you FOIL, that's what you get for the first guy, and then minus 5. Or, what is this equal to? This is the same as lambda squared minus 2 lambda minus 8. Okay, I do want to point out that the coefficient in front of this will always be a 1 or a negative 1. In this case, it's a negative 1 squared because it's second degree, so it's just a 1. Okay? Why does this happen? Because we have a minus lambda here that is getting repeated that many times when you do a determinant. Okay, so that's what this part over here means. Right? This guy that we pointed out back here, that's where this guy comes from in the theorem. Okay. All right. So now we need to set that guy equal to 0. So if I do lambda squared minus 2 lambda minus 8 is equal to 0, we notice that this thing does factor. We get lambda minus 4 times lambda plus 2 equals 0. And so we end up with 2 eigenvalues. Let me write them as lambda 1 is equal to 4 and lambda 2 is equal to negative 2. So we get 2. These are 2 eigenvalues. Okay? All right, so now with each eigenvalue, we need to find the eigenvectors. So let's begin with lambda 1 equals 4. So for lambda 1 equals 4, we're going to do a minus 4i augmented. This is what we need to look at. And so we take away 4 from the diagonals of the original matrix we started with. We have negative 1, negative 5, negative 1, negative 5, and then 0, 0. Okay. Now what? I'm going to multiply row 1 by negative 1. And if you recall, we've got what I referred to as the 2 by 2 trick. I know that the bottom is just going to become 0, 0, 0, right? And so we end up with 1, 1, 0, 0, 0, 0. Or you could do, negative 5 times row 1 plus row 2, and that'll give you the same answer. But again, this is like a shortcut when you have 2 by 2 matrices, okay? And you're looking for eigenvalues or eigenvectors. So what is the free variable here? The free variable is x2, right? Because there's no leading 1. And so that tells us that x2 is equal to t, and x1 would be negative t. So what do we end up with? We end up with negative t, which is the same as, if you pull a t out, it's negative 1, 1. Okay? What does this mean? This means that we have one linearly independent eigenvector, and that eigenvector is negative 1, 1. So what would the eigenspace be? E1 would equal the span of that vector. Okay, so that's how we write the eigenspace. What would its dimension be? Well, it's spanned by one vector, and so its dimension is 1. Okay? In other words, this is just a line through the origin. Now, keep in mind, the only difference from what we did before in 7.1 is we were throwing the 0 vector out, because 0 vector is not an eigenvector. But we are throwing it back in here just so that we can talk about this as a vector space, okay? So that's why it has dimension and all that stuff. Okay, let's do the next one. We had lambda 2 equal to negative 2. So we look now at a plus 2i augmented, which is equal to 5, negative 1, negative 5, 1, and 0, 0. So what do we do here? We're going to multiply row 1 by 1/5. So we're going to multiply row 1 by 1/5. And again, we're going to use the 2 by 2 trick. Or you could easily add, just add row 1 and row 2 together. Either way, you're good. You end up with 1, negative 1/5, and 0. And the other is 0, 0, 0. So, again, x2 is our free variable. We have x2 equal to t. What is x1 equal to? 1/5 t. Okay. And so what do our eigenvectors look like? It looks like this. T times 1/5, comma 1. So we have one linearly independent eigenvector. Now, I'm going to do something. I hope this doesn't confuse anybody. I'm going to write this instead as vector 1, 5. Now, why am I allowed to use that? Well, these are both, this guy is just a multiple of the other, right? So in other words, they're both eigenvectors. They're both in the same span, except this guy has no fractions, right? No fractions. And so it might be nicer to write our answer this way. There's nothing wrong with writing our answer with 1/5, comma 1, but I'm going to just eliminate fractions so that it's easier to think about, okay? So what this means is that E2 is equal to the span of vector 1, 5. This is our eigenspace. This is our eigenspace. Okay, what would our dimension be? Well, again, we only have one vector, so the dimension is 1. Okay, now what we've really been doing is we've been finding a basis. So just to make sure we understand what's going on, if we were to think back to our terminology of basis, we have two eigenspaces. So what's the basis for E1 equal to? Well, it's the vector we found for the last part, which was negative 1, 1, right? And a basis for E2 is equal to 1, 5. Now, let's use our terminology regarding A. N, so N is equal to 2 in this problem, and we have A has two linearly independent eigenvectors. So we have a name for that. This implies that A is non-defective. Again, we are using this new terminology all the time just to make sure that we get used to it. Okay? What do we notice here? We notice a few things regarding dimensions and all this stuff, right? The dimension of our eigenspaces, when you added them up, we got 2. And n was a 2 by 2 matrix. So let's write down a theorem that kind of summarizes what we've been noticing. So theorem. Let lambda I be an eigenvalue of A with multiplicity mi and eigenspace EI. And also let A be an n by n matrix. Okay, first thing, we already said this before, but I want to make this official as part of a theorem. EI is a subspace of Cn. That's the first thing. Number 2, what do we know about the dimension of EI? The dimension of EI is actually between 1 and its multiplicity. Okay, the dimension is always between 1 and its multiplicity. Why? Well, the smallest number of eigenvectors, linearly independent eigenvectors that an eigenspace can have is 1. Okay, when the highest that it could have is the degree. Okay, is the degree of this factored polynomial. So coming back again, remember what it means to have multiplicity. It means that when you look at this equation right here, this number up here is the highest number of eigenvectors that it might have for that eigenvalue. The lowest that it's going to have is 1. Okay, we don't know till we actually look for them, but that is what the theorem says. The theorem says that it's always between those two numbers. So we have a name for this, even though we were just calling it the multiplicity before. I want to say that mi is called the algebraic multiplicity of lambda I, and if Ni is defined to be the dimension of Ei, Ni is called the geometric multiplicity of lambda I. Geometric multiplicity. So we now have two types of multiplicities, the multiplicity of the eigenvalue and the multiplicity or the geometric multiplicity of the eigenvalue, right? Which is really the dimension of its eigenspace. The point is that the geometric multiplicity is always between 1 and the algebraic multiplicity. That's what this theorem says in our new language. Okay? So, let me give you guys a theorem. We're not going to prove this theorem, but we are going to state it. Eigenvectors corresponding to distinct eigenvalues are linearly independent. Okay, this is important because this means that the eigenspaces actually cannot touch each other than the zero vector, right? Because they all come from linearly independent eigenvectors. So, and they are distinct. They're linearly independent. So yes, they cannot cross each other. So let's go to a corollary of this. So corollary. The union of all linearly independent eigenvectors from every eigenspace is linearly independent. So if you take all eigenvectors from every eigenspace that are linearly independent, because of the theorem above, this means that they're all linearly independent from each other. And so we have a new definition. Or rather, actually, this is not a new definition, but let me formally write this down because we've been talking a lot about defective and non-defective. So we want to formally state this here because we are about to give a corollary. Okay, so let A be an n by n matrix. A is called non-defective if it has n linearly independent eigenvectors. Okay, in this case, we say A has a complete set of eigenvectors. This is a good thing, okay? So it is a good thing for a vector or for a matrix to be non-defective, okay? Complete set of eigenvectors. If A has less than n linearly independent eigenvectors, A is called defective. Okay. So this is our definition. So this leads us to another definition, right? We know that if you have n linearly independent vectors in Cn, these form a basis. For what? For Cn, right? And so we need another definition. If A is non-defective, then any complete set of n linearly independent eigenvectors of A forms a basis for our vector space. It's going to be for Cn or Rn depending on the eigenvectors that it has, right? We might get lucky and it might be Rn, but otherwise, worst case, it's just going to be Cn. We call such a basis an eigenbasis. Of A. An eigenbasis of A. Okay, so let's go ahead and before I write down our last corollary, I want to show you guys in our last example what the eigenbasis would be. So let's look at our last example here. Remember our two linearly independent, well, actually they're right here, right? This is one of my vectors and this is another one. We're looking down here. And so if you put them together, that gives us an eigenbasis. For what? Well, in this case, because they're all real components, it's going to be an eigenbasis. And it's for R2. So let me write this down over here. So in our last example, the eigenbasis of A is what was it again? Let's see, negative 1, 1 and 1, 5. And is a basis for R2. Okay, so it's a special basis. Look at it as a special basis of eigenvectors, and it's linearly independent eigenvectors. Okay, so this is our definition. So when do we know that A is non-defective? Well, there is one easy thing to know. When are we guaranteed to have enough of them? Well, if we look back at our theorem, we know that we always have the number of eigenvectors. There's at least one, but at most mi, and the problem is that mi might be bigger than ni, right? However, when are you guaranteed for that not to be the case? You're guaranteed for that not to be the case if mi is 1, right? Because if it's 1, then that means that you're going to have one eigenvector for every eigenvalue. You must, right? Because 1 is the minimum. So if all of them have degree 1, in other words, if the multiplicity of every eigenvalue is 1, then that means you know you're going to have a complete set. Okay, so this brings us to our next corollary. It says, if A is an n by n matrix with n distinct eigenvalues, then A is non-defective. Okay, again, let me just say really quick why It's because when you actually factor out p of lambda, it's going to be negative 1 to the n, and then every eigenvalue is going to appear exactly once. So because each of these eigenvalues has multiplicity 1, and each of them has to have at least one eigenvector, you know you're going to have n of them. And they're all going to be linearly independent by the last theorem. Okay? So finally, this gives us a nice case. If they're all different, great. But what do we need to guarantee it to be true? What we need is the following, okay? So if we come back here, we know this is less than or equal to mi, but the only way that we can have n of them, since all the multiplicities add up to n, is if these two are equal. We need this and this to be equal to each other for every single eigenbasis. In other words, we need whatever the degree of that polynomial is, we need for those to match. Okay? So let's write this down as a theorem. An n by n matrix is non-defective if and only if the dimension of EI is equal to MI for all I. Or another way to put this statement is that the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue. Okay, so this is what we need to be true in order for an n by n matrix to be non-defective. Okay guys, that concludes our video. We have one more section to finish up chapter 3. That's in our next video, section 7.3. Thank you very much for watching.